Hi guys, I'm here to explain about two theorems that are really important in the design of distributed systems that of course includes Microsoft architectures and systems. And they are the Cap and Pacquiao theorems. So let's look inside. We start with Cap theorem. Cap theorem was coined by Eric Brewer, a really well known and reputed professor and computer scientist. And CAP is all about a acronym of CAP, consistency, availability, and partition tolerance. And any distributed system will be impacted with these three properties for sure. So to design a distributed system, you have to look towards these three properties. So to understand the CAP theorem, let's take a look inside each of these properties so you can go to the theorem itself. What is consistency? Consistency means that any read made after the last write will return the same data, no matter the node that you are connected to. This happens because the data is in sync. The synchronization of the data was correctly made, and no matter the node, you get the correct and last data that is synced in all nodes. So if a system provides the proper consistency, you have the guarantee that you can read the data after a write. The data will be consistent. After that, we have availability. Availability means that a system is available for the client perspective. So if a client makes a request, the client will get a response back, no matter even if there are some nodes that are down or failing. For the client perspective, everything is just working fine because the whole system is considered to be available. So this property is called availability. But in case of availability, data may not be in sync. Data may be unsynchronized because if some nodes were down, for example, how can data be in synchronization with all nodes? That's not a guarantee. So from the client perspective, the whole system is available, but the data may be not in sync in this case here. And the last property is partition tolerance. So what is partition? First of all, what is partition? What is partition tolerance? Partition tolerance means that the system continues to respond even if some communication breaks in the system. But for the client perspective, the client doesn't see that. All requests are fulfilled and the client get a response back. So for the client, everything is just working fine. But in the backstage, maybe some broken the communication just happened. And a system is considered partition tolerance if partition happens and the communication and transparency still goes for the client. So let's see this image here. The partition, for example, network connection just break. The nodes are still responding. The client connections can be made in each of the nodes in this example here. Communication can still be later recovered, of course, between the nodes. But again, data may be unsynchronized. That's because if communication is broken, how can synchronization be done? So a system is considered partition tolerance if communication goes through even with some breaks in the communication between the nodes. So those are the three properties that we have to consider in the CAP theorem, okay? Now about CAP theorem itself. What is CAP theorem? CAP theorem states that a distributed system can only provide the two of the three properties at the same time. So no system can provide the three guarantees at the same time, only two of them. So that what the CAP theorem states here. And that really generates the kinds of systems that you're going to see here. So this is a diagram that really states the kinds of the main well-used systems that you use and are, of course, distributed by nature. So you have a database here, and if you go beyond this slide, you can prove that that's the case. You cannot accommodate more than two of the properties at the same time. Let's prove it. So you have a CA system. What is a CA system? A CA system guarantee consistency and availability because you have the C and A letters. So if a system is considered to be a CA system, consistency is guaranteed so I can read after the last write, and availability is guaranteed too. Every time that I access as a client perspective the system, I get a response back. But if partitioning happens, it's not possible anymore to keep consistent because how to synchronize data if a node can't occasionally communicate with the other node? So the P letter is not available here, only C and A. And we have examples here of the almost all relational database. They guarantee consistency, mainly, of course, the ACID properties of a relational database. They guarantee availability. The system is up and running, but partitioning is not guaranteed at the same time. If you look at another system, you have the AP system. AP systems are about availability and partition. Even when partitioning, breaking the communication, something like this happens, clients can communicate with the nodes. So as that earlier image that I shown, communication is made to the nodes, but some communications break down. The client does not see this. It's in a transparency that things happen. However, as a result, they might not be consistent at all times because if partitioning is happening, even if I can connect to distinct and different nodes at the same time from the client perspective, how data can be synchronized if a break in the communication is made in the backstage for the client? The system can be in an inconsistent state. And we have some kinds of examples here. Also, we have a CP system. CP systems are systems that are considered consistent. So again, you can read after the last write, you get the same data back. And partition tolerant. They guarantee consistency and also communications with clients even when partitioning happens. However, when partitioning happens, some nodes may be unavailable because as you can see in the example with MongoDB here, let's understand how the CP system uh, is about to happen here. As everyone knows, MongoDB is a NoSQL database and a CP system in the CAP theorem. So strong consistency is reached because this system is consistent, right? And how is done? How is it done? By using a single master node for the write operation. So Mongo can be partitioned without losing consistency. However, when partitioned, some nodes may become unavailable. The system won't accept write requests until it makes sure that all operations will be saved safely, or it shuts down the partition node for a while until reestablished. So let's think, for example, that some node is failing or going down. As the read and write operators go through the master node of MongoDB, the Mongo guarantees the consistent state, the consistent reading of data, even if communication is broken, even if some node is going down or failing. Because of this approach, MongoDB guarantees the C, the consistency, and the partitioning possibility, but not availability, because the node is failing and it's not available for connections, right? So that's how MongoDB is stated as a CP system here. Consistency and partitioning is allowed, is really allowed, but for a short period of unavailability of the sum of the nodes by the node itself, by the server, or by the communication that is broken between the node and the master node. So that's why MongoDB is considered a CP system. So it's really evident that knowing cap theorem is essential to design a distributed system. And what about eventual consistency? We are talking about consistency here. Eventual consistency really happens for a distributed system. And what does that mean? Eventual consistency means that consistency can occasionally take some time to happen. So note, the system is still considered consistent because, of course, you can read, get the consistent data, consistent state after the last write. But in some case, you have a kind of eventual consistency. It takes some time for you to get the data, the correct data back. Of course, this data will be back for you at some time, some later point in time, but it can take some time. All times that this happens, we call it eventual consistency. And mainly, this happens because of synchronization time. In distributed system, every time that you have synchronization data, you are up to sync time, and sync time leads us to the eventual consistency. That doesn't happen if a system can guarantee this management. That's the example that I just mentioned about MongoDB when you are going through the master node, and the Mongo guarantees they strongly consistent for you. But in case that you have to read for other locations without this kind of approach, we are really up to the syncing time and, of course, eventual consistency. So let's give another example by MongoDB itself. As I mentioned, MongoDB is strongly consistent by default. So if you write right now, you can just read the data that was written in Mongo because of the single master node approach that Mongo uses. But as many know here, Mongo really allows you to enable secondary reading from secondary nodes. And this is called read replicas. And every time that you enable secondary replicas and read replicas, so you can connect with a read replica directly, of course, now you are up to the eventual consistency because you're not going for reading, just for reading. You're not going through the master node. And by this, we are elected for the eventual consistency because you have to consider the synchronization time between nodes. We are going to the read replica directly, so you have to consider eventual consistency. So going to the masters, MongoDB is strongly consistent by default, but going direct to the read replicas, you really have to consider eventual consistency, a consistency that can eventually or occasionally not exist, but will, because the system is considered consistent, by the way. So that's the eventual consistency concept here. And by now you can see that considering the cap theorem, considering consistency, availability, and partition tolerance is really important in the design of distributed systems because they just happen to be accommodating any kind of design of distributed systems. So you have to know, you have to consider the cap theorem. But of course, you have to go beyond because as is already known, you have the Pacquiao theorem by Daniel Abadi. There is a kind of critic to the cap theorem, and you're gonna know why here. The Pacquiao theorem states that CA, AP, and CP systems or concepts are not enough. You have to look beyond them. So as you can see here in this diagram, if there is a partitioning, how does the system trades off between availability and consistency? So as you can see, it's not just about CA, AP, and CP concepts themselves in the CAP theorem. Now you have to look beyond. This diagram states the Pacquiao theorem, and it starts with partitioning. And if you ask the system is partitioning, there is some kind of break in any kind of communication between the nodes. If the answer is yes, we still have to consider availability and consistency and one versus the other, because uh, if the system is partitioned, is it available? That's a question. And if it's available, is it consistent? The data in a consistent state? Maybe not, so I have to consider that. Going to another direction, let's suppose even if the system is running normally, everything just works fine, so it's not partitioned, so the answer is no. But what about latency? Because the system can just be running normally, but the latency is so high that the consistency is about to be a question for everyone. Because if latency is high, the data is consistent in a consistent state? Maybe not, because of the eventual consistency. So it's really not just about the cap theorem. You really have to look beyond this theorem, because everything here is just feasible. It makes sense, and you have to look beyond this. So as I just mentioned, it's not just about cap theorem. You have to look beyond it. You have to consider partitioning, if the system is partitioned, yes or no, and you have to consider the other attributes mentioned here to design your system and prepare the system. Really looking towards all those aspects mentioned here. So in summary, in my opinion, a designer of a distributed system has to look towards both theorems, because both theorems are really important here, distributed system. So what I really recommend for you is that you don't have to hesitate in looking towards both theorems, because they are really important to design a distributed system. So you have to consider them to understand the behavior and the consequence of your choice, architectural choice, of course. And this also applies for microservices too, because they are considered distributed systems by nature. So that's it, guys.